For this problem, we have two cylinders that have the same center, and the inside cylinder is rotating at the speed of omega O, and then the outside is not moving. The inside radius is, we're going to call it Ri, and the outside radius, we're going to call it Ro. And we can instantly know that the velocity of the fluid, which is just on the outside parameter, when the radius is Ri, we're going to know that this is going to be same as the double omega, since it's rotating, and on the outer, and when R is equal to Ro, it's going to be equal to 0. So what equation should we use to begin with? And as always, we need to ask what kind of coordinate system we should use between cylindrical and rectangular. And because we're dealing with cylinder, it's going to be, of course, cylindrical coordinate. And then among cylindrical coordinates, we have to ask at what direction is the fluid moving. And because the fluid is rotating this way, we know that this is going to be and because of that, the velocity profile is roughly going to look something like that. Where it is faster as it goes inside. So we know that the velocity profile is changing by the radius. So we're going to choose an equation among the cylindrical coordinates, the one that has like a VR. And as usual, the left side cancels out because it's fully developed and one-dimensional and steady state because it's t. And on the right side, we're gonna, because the velocity profile is changing by the radius, we're gonna keep this one. And this one, this is gonna be equal to 0 because this theta is referring to the angle, right? The angle going from here to like here, and regardless of the location of the angle, the velocity doesn't change. So it's equal to 0, and z direction, so it's going out of this way, and that's not going to change. So that's going to be equal to 0. And same for the same principle, this theta is equal to 0, as I said earlier here. And dp over dr, this is not pressure-driven system, this is also equal to 0. And there's no effective gravity on this system, so it also equals to 0. What we have left is 0 on the left side, and then mu, the viscosity, and this stuff over here. And we can solve it out. Divided by mu, then we'll get 0 and this stuff, and then we can take the integral, and we'll get C1, some constant, and what was inside over here. And we take integral again. After we move the multiply by r on both sides, we'll get C1r, and then this stuff, and we'll take integral of them, which will get C1 over 2r squared plus C2 equal RVR. And then we can divide it by r again, and we get that. And as I said earlier, there's two boundary conditions that we can use. When r is equal to Ri, the inside, where the velocity will be equal to omega O, which gives us this equation from here. And then another boundary condition where r is equal to Ro, here, the velocity is going to be 0, right? So it's equal to 0 and that. And we can do some system equations, and I didn't solve it out all the way because it was taking a long time. But once you solve this, I'll solve for C1 and C2, and we have two equations, so we can solve this out, and we'll get some symbolic form that complete this velocity profile equation in this system.